I'm professor in the Faculty of Pharmacy, and my research line is the analytical chemistry. So my lecture will be about chemometrics fundamentals and some applications. And I don't know the level of chemometrics of the persons here. I think that there are maybe some knowledge of someone, but I will try to give a rapid overview of the variety of chemometric methods that we have in order to think after the presentation of these days, to think in which method maybe we can apply in the project. So I will start my presentation talking about the definition and some background of chemometrics. Then we will see some classification of chemometrics methods, because chemometrics methods can also be classified. And one kind of methods in chemometrics are called pattern recognition or classification methods. And we will see then some quantifications, application of multivariate analysis, and other techniques like curve resolution and multi-way methods to see the board of the variety of methods that we can use. About definition and the background of chemometrics, some about history of this young topic. I want to tell you that the chemometrics notation was introduced by first time in 1972 by Svante Vold from Sweden. And he was working in the application of mathematical, statistical, applied to the analysis of chemical data in Sweden. And he met with Bruce Kowalski, who was working in the same, but in the United States. And after 4 years, the International Chemometry Society was founded. I know that Kowalski asked to Vold, what are you doing in the Analytical Chemistry Conference, International Conference? And Svante Vold said in a fast answer, oh, I'm doing chemometrics. In this world, it's applied until today, okay? The use of chemometrics was expanded in the 80s with the beginning of the availability of personal computers, and some initial applications were used in QSAR, quantitative structure activity relationships, and also the evaluation of the first analytical applications using chemical data. But actually, chemometrics is used in a lot of another areas, including chemistry, but also like computer-based laboratory, handling of chemical and spectral databases, and also artificial intelligence. So, but what is chemometrics exactly? Chemometrics maybe can be defined by the combination of several areas like mathematics, chemistry, and statistics. Some definition we have here, some definition, for example, the definition given by the UPAC. And UPAC say that chemometric is the application of statistics to the analysis of chemical data from organic, analytical, or medicinal chemistry, and the design of chemical experiments and simulations. And another maybe recent definition of chemometrics given by some recognized professor in Germany is that the chemometrics is a chemical discipline that uses mathematical and statistical methods to design or select optimal measurements, procedure, and experiments. This part of chemometrics is now experimental by design, or to provide the maximum chemical information by analyzing chemical data. So maybe this is another definition that chemometricians use, and maybe it's more explained with this torture the data until they confess. So, but when, how, and why we need to use chemometrics, I want to remind you the analytical process flowchart. This process begins with a sampling step, and then the sampling or the sample or the obtained samples are submitted for a different pretreatment. Some techniques requires more pretreatment, and some techniques like, for example, NIR that we saw in the morning early, does not. So in this step, sample pretreatment, for example, we can apply some chemometrics methods like the experimental by design methods in order to optimize the response of a future analytical measurement. So here, even in the sampling, we can use experimental by design too. So the analytical process has a lot of stage where we can apply this kind of methods. Okay, and then we have the analytical measurement in spectroscopy, for example, over spectra, and the spectra will be submitted to the data analysis using most of the well-known chemometrics methods. So maybe this stage is the most easy for us to work, because here we need another kind of method that is basically firstly in the experimental work, and here's the data analysis is the computer work basically. Okay, and then we have to obtain the relevant information about our data, and this information can be used for quantification, for cluster evaluation, groupings, classification, or only to see if our sample has some correlation between samples, or even if we have to note if we have variables and sample correlation and so on. And the question, why to use chemometrics? I say my students all the time that the question will be, why not to use chemometrics? Because chemometrics has some advantages, very important advantages regarding the use of monovariate analysis. And maybe the principal characteristic of the result obtained by chemometrics is the improvement of the selectivity. So this point is very important for us because we can avoid the separation or interference of our samples in order to work mathematically the data coming from the analyte, the interest analyte, with the interference. So we sometimes don't need to work too much in the separation of the analytes. So it reduces cost of analysis, also decrease the effect produced by the matrix of the sample, and then we will have an improvement of the prediction abilities of the analytical technique that we are using. So with this kind of methods, we can answer some questions like the question that you have here. For example, can the spectral features of vegetal material indicate its taxonomic species? Yes, it was answered some years ago, and yes, that's true, it can. Okay. Is the chromatographic profile of WISE used to assign its process? Maybe yes, maybe not. Maybe Ivan knows more about that, but maybe chromatographic profile can be used for assign the processes. Can we quantify? I'm talking about now quantification to active receivers in a pharmaceutical tablet. If this have overlapping signals, we think yes with the use of chemometrics, yes. Even if we have overlapping signals, it can be possible. Mario knows that because my student Mario there worked in that. It's possible to predict the ammunition brand using the spectral profile of gunshot residue? Yes, I think. And so on, a lot of questions that we can answer with this type of techniques. For example, it is possible to differentiate the sugar source of a SuChAQuality sample using vibrational spectroscopy techniques? Maybe yes, using chemometrics. Oh, I hope so. So chemometric methods are known or called also multivariate analysis methods. So these methods has a sequence, and this is a suggestion, but we can follow this sequence in order to have better results and see our result in each stage of this sequence. Okay. The first step is the problem definition. We need to know what is the purpose of the analysis. If the analysis will be quantification, for classification, or we are looking for only a signal separation, if we have signal with overlapped bands, for example, and we must to be sure about what we are expecting about the use of chemometric methods. Then we need to array our data in a matrix. We use, most of methods use a matrix, and for this reason we need to know about a little bit matricial algebra, and then we can visualize our data. The data will require a pretreatment mathematical, and this stage is very crucial because we eliminate here the noising, for example, or another not desired interference produced in the acquisition of a signal or data. And then it's maybe mandatory to do exploratory analysis. In this stage, we use the most famous chemometric method. It's the principal component analysis, PCA. Michael talked about that. And this step could detect anomalous samples called outliers. And in this step, we will see if we have some correlation between the samples or between the variables or sample with variables and so on. Then we have to decide the way of the analysis. If the way is classification, I will go to the pattern recognition methods. If the way is quantification, I will go to the calibration methods, or if the way is to optimize the best conditions to enhance our response, we will go by the experimental design methods. Then we will have a mathematical model with predictive ability in some cases. In cases of classification and calibration, we will have a mathematical model with ability to predict the class or the concentration, for example, of a future sample. But this mathematical model will be validated first to use this model for the prediction of future samples. So this is the stage imperative also to use the model for future predictions. Okay, regarding the problem definition, we need to be sure about that we are looking for classification, quantification, optimization, signal separation, signal improvement, and we have here a lot of kinds of methods for multivariate analysis. So if is classification my problem, okay, I will go to the pattern recognition, quantification, multivariate calibration, optimization, experimental by design, signal separation, curve resolution, signal improvement, signal processing, okay? So I can define the tools that I need to solve my problem. Then I need to array my data, and the data is arrayed in a matrix where the rows are concerned to the samples. Each sample is a row, and the columns will be the variables, wavelength, frequency, elution time, if it's chromatography, or maybe concentration. So I have a matrix. For example, this first element will be absorbance of the compound of the first sample for the first wavelength, okay? And this sample will be the absorbance of the first sample to the second wavelength. So, okay. We can have discrete or sequential data. What does mean that? Discrete data means that we are using concentration, physical properties, or any property that could be acquired using different analytical techniques. For example, I have here a matrix with different properties in the analysis of some sample vegetal in order to determine the yield, but they are using a lot of chemical components obtained by different analytical techniques, okay? So the range of values are absolutely different. And this kind of data will be submitted to a specific pre-processing techniques, because we have now the errors coming from each analytical technique. But it's different in the case of sequential data like spectra and chromatograms, because we have the information of each column coming from the same equipment, from the same instrument in most of cases, because we can also have a data fusion, but this is another situation. So I want to talk just about the sequential data when the signal or response of the measurement is based or follows a function, for example, the spectra in function of the wavelength, or the chromatograms in function of the time rotation. So I think in this project we will use more this kind of methods, because we are proposing the use of some vibrational spectroscopy and also other molecular spectroscopy. So we need to see how is our data after data acquisition or spectral acquisition. For example, here we have a NIR spectra from different samples, from different species of wood, but they are very, very similar, excepting by this dispersion. And we can see here in this visualization of the data, if the signal obtained at different wavelength has relationships. For example, he said just four wavelengths, and we can see that they are very, very, very correlated. And this is a problem for analysis of data. It's called collinearity. And collinearity is a problem to be solved in the or during the pre-processing and transformation of data. Okay. So in this case, a specific case, we also see some anomalous response of the samples produced by the size of particles. And we can see that because we have this scattering here, and it will be solved by using some methods, or also chemometrics methods, like correction by multiplicative scattering correction. So we can see if we have some anomalous samples or layers, but in this case, I don't say that. And we can see in this stage if we have an adequate response of the, for example, absorbance or transmittance or reflectance and so on. So this is an inspection of our data, and it's very, very important to follow the sequence of the multivariate analysis. So when I detect some problems in our data produced principally by the spectral acquisition or the instrument, the noise, we need to use transformation or pre-processing in order to solve these problems and have a very good signal before to be submitted to the chemometric for classification or calibration. So we can apply transformation methods if we use some mathematical strategies that affect the rows of this matrix, and we affect the columns. We will call these methods like pre-processing methods. So there are a little difference between transformation or pre-processing. Also, most people say pre-processing to everything that we apply to the data. So we must to remind the signal is a sum between the true signal plus the random noise, and this random noise will be eliminated from our data, and we will work with this true signal, and this true signal will have relevant information, very important for the analysis, but also we have irrelevant information, well acquired, correctly acquired from the instrument, but it's irrelevant because maybe belong to the OIS format or is produced by the interference. So we need to minimize this irrelevant information. Okay, so we have two kinds of contribution, deterministic and stochastic, and so we will use some methods in order to remove this stochastic contribution using smoothing techniques, and we will reduce the effect of deterministic contribution using baseline correction techniques in case of a spectrum. So here we have some methods used to improve the signal obtained from an instrument. The most famous are the smoothing techniques, derivatives, baseline correction, multiplicative scattering correction, standard variant normalization, so on. But we can see the effect, for example, in a fluorescence spectra obtained here by microscopy of fluorescence. And then if we have smoothing, you can see here the difference that we have regarding this kind of method. And then this spectra or smoothed spectra can be submitted to a chemometric analysis. Derivatives is used if we have two kinds of problems. First, dispersion, or a second, overlapped bands. So if we have overlapped bands, for example, we need to use the second derivative spectra before the analysis. Also, use of spectra change the shape of the bands. So chemical interpretation after that, it's a little more difficult. And the case, for example, in the second derivative, if we have a strong band like here, we will have then a valley in place of the top. So derivatives increase noise. So we have to maintain an equilibrium between the use of derivatives, for example, in order to avoid the noise, but with good result to separate overlap bands or peaks. So if we have dispersion of light, like the results obtained by use of near-area spectroscopy, by reflectance, diffuse reflectance, for example, we use multiplicative scattering correction or standard normal variates. So we solve this kind of a spectra in with these results, okay? And if we have influence of the amount of sample, we can use normalization. For example, if we are working in chromatographic, the amount of sample can be affected, and so we can use normalization. In the case of spectroscopy, we can also normalize. Maybe you know that technique in mid-infrared spectroscopy, the use of KBR pellets. So the thick of this pellet can be solved using normalization, so you don't need to weight the KBR or the samples, just to apply mathematics. No? And we have here some tools used, computational tools and software used for analysis of data. Most of applications are developed in MATLAB in turn, and you can find a lot of algorithms and routines ready to be used for MATLAB. And Pirouette also a good software, especially for classification, and Scrambler too. Classification prediction, Pirouette and Scrambler. Agent Vector has a PLS toolbox, very famous, because you can see exploratory analysis, also classification, also calibration, and so on. And I want to show this very interesting softwares, MVC1 and MVC2, for calibration or quantitative analysis. This software is free, it's developed by an Argentine group, or Professor Olivieri, and it's very analytical. So we will have here analytical figures of merit that is not easy to be calculated when multivariate methods are used. So this is another good toolbox, is multivariate curve resolution, very famous, from the Universidad de Barcelona group, and we are available also free in internet. So now I will talk about the chemometric methods. Sorry, it was moving. But here we have the principal component analysis, because this is the exploratory analysis for excellence. Used it a lot of time ago. And we can divide the methods in many groups. I have a division in 5 groups. The first group corresponds to the exploratory analysis and pattern recognition methods to obtain classification or classes of samples to assign a class to a new object. And the second one is the calibration methods. The most common maybe is the partial least square, PLS. And here we have first order, second order, third order, and so on of calibration methods. Then I will talk about that, but only to have in mind if that the most common used for a linear regression method is the zero order regression. This is the most or the simplest way to give a regression. If I use an X variable and Y variable and I did a regression, simple regression, I'm using the zero order. And when I use not only one variable X, but a lot of variables in X, I'm using first order. And this is multivariate analysis. If I use it first order data, I will have a matrix, but it will have another kind of method for second order. I need a cube of data and so on, okay? And then we can see also the calibration method has as purpose the quantification of components, okay? The third methods could be the curve resolution methods. Here the objective is to separate signals, overlapping signals, but it's not only a separation, a mathematical separation using, for example, derivatives. No, it's a more sophisticated method which use use the concept of exploratory analysis, but using constraints to obtain chemical meaningful results. Okay, then we can we see the experimental by design methods where we will be able to optimize our response. If, for example, in the say preparation of one compound, if we have some concentration at determinate temperature with rotation times and so on. Okay, this is another kind of method we can also discuss more, maybe in the School of Chemometrics, more about that. This presentation will be focused in the exploratory calibration and classification methods. So, and another kind of methods is the signal processing and time series analysis. And this is another word, digital filtering, smoothing, signal derivatives, Fourier transformation. I think the class of yesterday was very related to the signal processing and time series analysis. So Fourier is the expert here. No? So, now I will talk about the exploratory analysis, and today Michael talked about that principal component analysis as a principal method that we need to use, especially if we are working with some technique like near-infrared spectroscopy. So we can think in principal component analysis using the concept of matrix, the X matrix that I defined before, because this matrix will have one sample and J variables, and these variables can be the rotation times or the wavelengths. If we are talking about near infrared, for example, spectroscopy, we can talk about the wavelengths. So you can imagine how can you plot this data or this matrix using the J dimensional space, using all the variables. It's very complicated to imagine this plot data, because you can see, for example, here in this plot, the plot of the samples of one set of data, if you have variable 1 and variable 2, and the samples will be here, okay? But just using var 1 and var 2. But near-infrared data can be formed by thousands of wavelengths. So imagine graphic representation with all these variables. This is the J space, okay? And it's very difficult, but it's possible. And this is that I see in this graph, banana, for example. This is the distribution of the data with a form of banana in the J multidimensional space, okay? Yesterday we have a pear, today is a banana. I don't have a banana, but I think that I can use something else. I will use my phone or something. Please tell me no. And this is our data and have this shape of the, I imagine that this is a banana. And this is the matrix, and PCA will decompose our data into matrices. This matrix will be called scores, and it will be related to the samples. And this matrix we call the loadings, is related to the variables or wavelengths in this case. So, and we have another matrix called residual. So if the noise, is the irrelevant information will be there, okay? So this is the distribution of my data. In statistical, the distribution can be explained by the variance. So I can say, I can define some vectors, call it components or principal components, and these vectors will be a linear combination of the original wavelengths in the spectra, and try to describe the most information of the most informative vector of this data. For example, here, PC1 will be the vector which recovers the maximal information of my data. It will be this axis, okay, in this direction. So the second most informative vector will be orthogonal with the first. So we can see here the second component, and the third component will be the next maximal variance explained in this distribution of sample. In this case, this direction. No? So first, second, and third direction, and it will be the new spatial dimension of our data. I said that. So if we have a J space, now I have just 3 or 4 or 5. So PCA is a reduction method because reduce the dimensionality of our data to new variables called principal components. Okay. Okay. Now I will plot my samples regarding these new variables called principal components. So this is my sample in the new plane. This is the coordinate PC1 and PC2, and I want to measure this distance regarding to this is PC1 or regarding the sample 4, for example, regarding to PC2, and this value will be here in the scores matrix, okay? And give me information about the samples. And the loading matrix, the elements of this loading matrix will be the cosine function between the angle produced by the PC with the original variable. For example, here have the angle formed by the PC1 and the variable or wavelength 2 for one sample. Okay, the cosine of this angle can vary between -1 and 1, and so we will have these values between -1 and 1 here in the loading matrix, and this value will be give me information about the importance of the wavelength or variable for the PC1, PC2, and so on. This is the linear combination that we have. The PC1, for example, is a linear combination of wavelength 1, 2, 3 multiplied by a coefficient. This coefficient is this loading, is this cosine of this angle, and if we have a higher value here, this variable or this wavelength will be important for this component, okay? If the value of this coefficient is very low, this variable has no importance for this PC1, for example, okay? So we can see here which variables are most important for each PC. And the PC also can separate our samples in a new spatial dimension. And the PCs are represented by a vector called eigenvector, which has associated an eigenvalue used to estimate the spline variance. What is that? It's basically an information, the percentage of information that we recover of our data with new variables. I mean, if I have J variables, I will have the 10% of information in my samples. But if I reduce these J variables to 3 components, principal components, maybe I will not have that 100%, but I will have 90%, and it's so good, okay? Maybe it's low, it's 20%, it's very low, so I have to try to get more variance or more information using another reprocessing techniques to improve my results, okay? So this is an example, a couple of samples from PCA application. And I have here two, sorry, I can see here. Okay, and I can see here 2 examples for sample differentiation of wood species using near-infrared spectroscopy. I have here one problem. The problem is that we have wood from eucalyptus. The eucalyptus has here in Chile 2 species, Eucalyptus globulus and nitens, but they have a very different properties regarding climatage and cold resistance, and also yield. To the forestry companies needs to know, to be sure about the species that they are buying to the producers. No? And they use near infrared, and we can see here that we apply different pre-processing techniques in order to see, after application of PCA, if we have difference between the spectra or not, and what is the best pre-processing technique to see this difference. So here we have good separation of the species, globulus and nitens. Here too. Here, no, not so good, and it's maybe acceptable. So, but it could be the best. Why? Because I can see here that with the PC1, I have 31% of variance, of spline variance. In a total, using PC1 plus PC2 plus PC3, in this new spatial dimension, I will have around 66% of spline variance. So with this method, using maybe this kind of derivative, second derivative, I have just 12%, 8%, 33%. So I can conclude that near spectroscopy is a good tool to differentiate these wood species, but we can improve, but maybe it's enough for analysis in order to see if the analytical technique is useful. So at this point, we cannot classify a future sample because this is a only exploratory technique. It's not a classification technique. Classification technique will be able to predict the class under some other conditions, okay? I'm looking for the sample only with the use of PCA because I'm using only X matrix. No information about the class of each sample. I put a color, but I didn't not use the information in the mathematical analysis, okay? So here we have another application. It's a differentiation of algae species, hemorphologic structures by mid-infrared spectroscopy. Here we have, for example, so 2 species of algae. We have Macrocystis pyrifera and Lesonia spicata. This is Lesonia, and all the samples are Macrocystis. We reduce the space of the mid-infrared spectra to 2 variables, call it principal component 1 and 2, and we can see here the first component separate the sample, so we can conclude that this this principal component is that important to see the difference between the two species. But also the second component separates some samples from the same species, Lawsonia, but here we have Lawsonia obtaining in summer, and here's the Lawsonia, oh, sorry, this is Lawsonia, this is Macrocystis, Macrocystis obtaining in winter and spring. So the second component could be separated by the season, okay, the samples by the season. And now we are looking for an explanation for that, and we can see that loadings plot simultaneously using the same coordinates, PC1 versus PC2, and I can detect here who band is responsible of the separation. For example, here, this variable has a high loading regarding to the PC1 because the distance is high. So the same in the case of this band is very important to the PC2, okay? So I can identify which band is responsible for this separation. How can I do this interpretation? For example, these bands assigned to carbohydrates are related. This band to these samples, and this band, and this band, and this band to these samples. And the group here is principally described by this band, okay? So we can make an interpretation of who is responsible of the separation. Here's the same case, but using different morphologic structures of the edges. You see, for example, aerosystem tips regarding fronts, and we can see some difference. If we can assign who bands characterize this group, who bands characterize the other groups, okay? So this is the information that we can obtain about principal component analysis. Here have another one, is the determination of some mineral species, but by another method. It's not a molecular method, but it's an atomic spectrometry by laser-induced breakdown spectroscopy, just in order to see how PCA can give us information about the separation of samples or groupings of samples, spontaneously separation, using different analytical techniques, like in this case, a technique which is spectra formed by lines in place of word bands. These lines, and we can detect which lines, for instance, which element is responsible of this differentiation of the mineral species. So I have another example. This is one paper with the objective to use PCA or chemometric methods to see if there are differences between botanical and geographical origins of the cocoa beans in the branch-related formulation and processing. Here we have two analyses. First is a PCA in order to find if the separation of samples produced by the bean genetic group, specific cocoa bean genetic group, it's possible, and we can see very acceptable, maybe criollo in este caso, sorry, criollo in this case is absolutely separated from the other two kinds of samples, but between these samples, the separation is not so good, but maybe it could be improved. So if we have good results with PCA, we can follow with the next stage, is to use another classification method in order to make a mathematical model used for future predictions, okay? There are supervised methods based on PCA. So we try to look at them. So this is the same, but exploration is just by single geographical origin. Latin American and South African samples will be compared if we can see spontaneous separation of samples using only the spectrum. Okay, so if we have the samples with good results in PCA or another exploratory analysis, PCA is not the unique method used for exploratory analysis. We have also hierarchical cluster analysis or the famous dendrograms used for this step too. So if we have those results in these exploratory steps, we can follow the way of the supervised pattern recognition methods. Okay, and these supervised methods could be different, and the mathematical and statistical fundamentals are different between all these methods. There are a lot. I have here 5 methods. I will describe a couple of them, but the most known methods are the discriminant analysis, which requires a normal distribution of data. This is imperative, this is mandatory. The KNA method, the key nearest neighbor method, is a very simple method to be used. Use it. The self-independent modeling class analogy is SIMCA, support vector machine, and linear learning machine. In chemistry, maybe the 4 first methods are well known. But the super pattern recognition methods can also be classified according these criteria. For example, if the method is parametric or no parametric. If the method is parametric, we can assume a normal distribution like SIMCA, for example, but KNN does not require the normal distribution. A discriminant method can belong to the sample or just to a single class, but a modelative method can belong to one class, to more classes, or to any class to SIMCA. This is an advantage of this kind of method, because if we have one sample and if this sample is modulated regarding 2 classes, and if this sample is not coming from any class, the method will give us this information. Okay, and also if the sample belong to the both classes, because it's also possible. Okay, so the methods could be also probabilistic and deterministic. If we have a confidence level like SIMCA, we have a probabilistic method, and if we don't need a confidence level, KNN will be KNA will be used. Okay. So in the case of classification methods, we need the X matrix, but we need also another information about our samples. For this reason, the methods are called supervised methods. We need this matrix or vectors with the information about the class of each sample. For example, here these vectors say that the first row correspond to a sample of the class 1. The second of the second, the third of the second, and the end to the class 2, okay? We can also express the same in a matrix notation. This is the class 1 column, class 2 column, and if it's yes, it's 1, if it's not, it's 0. So some software use this kind of input for our classes. So now we are using 2 matrices or vectors for input in the supervised methods. This is the definition of the nearest neighbor, the K nearest neighbor method. It's a method based on distances between samples and groups in the space J-dimensional. And a brief explanation of this method, for example, can be applied to the class assignment of this X sample. Here is my sample, the problem, and here I have 3 classes, class 1, 2, and 3. Okay, so this method will calculate the distance. Normally, it's the Euclidean distance, which can also the Mahalanobis distance, but maybe the Euclidean is the most used. And this distance This distance is calculated for each class. For example, here this is the nearest neighbor of this class. So this is the distance. I'm looking for the nearest neighbor in this class. This is the sample. So I calculate this distance. And here I'm looking for the nearest neighbor of this class. And this is the sample. And I calculate this distance. Okay. The shorter distance is that. So this class wins one vote. Okay. And then I will repeat the analysis using the next nearest neighbor, okay? And the class which wins have another vote. And then the matrix of votes will give us the class of the assignment class of the X sample, okay? So it's easy. But here we have just one nearest neighbor. It is to calculate. And maybe the advantage of this method is that this model has flexible boundaries. So we don't need a function, mathematical function, linear function, quadratic function to be found to separate the samples. So we can hear samples for one class in the other group near to the other samples. But that's no problem, okay? Because we can construct or build the flexible boundaries. But this method depends on number of classes, or samples, sorry. If we have here 20 samples and here 100 samples, it will be, maybe, it will not work good, okay? So this is another method, it's SIMCA. SIMCA is a supervised method based on PCA. So this is KNA is a method based on the analysis of dendrograms because measures distance. So SIMCA is a supervised method of PCA. Okay. How works SIMCA? SIMCA builds a PCA analysis of each sample. Each class, okay? So if we have, for example, here 3 classes, we will make a PCA for each set of samples of each class in order to have these class books for each class. This class box has a cloud of probabilities. And also this cloud probability will have the boundaries by a value of variance. Okay, this is we need to calculate a critical variance at a determined level of confidence, and this critical value will be used to assign the class of future samples. For example, here we have the critical variance of the class 1. Here have we the critical variance of the class 2. Here also, these lines are the critical variance. And then we must to calculate the variance of each sample, because each sample can have a variance. And if this variance is under this critical value, the sample belongs to this class. Okay, for example, here, if my sample is here, is below the critical, is under the critical value, so belong to the class 1. If the sample is here, it doesn't, okay? And if the sample is here, is not under the critical value for class 2, so the sample cannot be assigned to the class 2, either to the class 1. So we have 4 quadrants here. This is the case when the sample belongs to both classes, to any classes, this quadrant, just to class 1 and just class 2. And this is the advantage of SIMCA to be a modulative method which can give us the information about the classification of the samples. The samples are Eucalyptus, again, Eucalyptus globulus and nitens, and we work with a forestry company with a sample that this use leaves, but in the case of wood, the sample was classified here So we repeat the analysis. And then the first component said as the sample, it's a mixture between globulus and needles sample. So it could work. It's okay. This is a projection of class. SIMCA has, in another classification method, has some parameters to evaluate the success of the method. So we can see here one of them. This is the projection class, and the class has here the boundaries at 95 or 99% of confidence level, for example, and we can see if some classes have overlapped confidence region. And also we evaluate the confusion matrix. This confusion matrix will give us in the diagonal the elements which are correctly classified, okay? And we can also calculate another parameters like the sensitivity percentage to know if our samples are correctly classified. So this is regarding the SIMCA, so I will talk about quantification methods. Now I want to show you some application of multivariate analysis for quantification and other techniques. And regarding quantification in analytical chemistry, quantification methods and calibration in analytical chemistry, I want to show you this picture because it's very famous in calibration. Because we need to know in which level we are working with a sophisticated instrumental equipment that we have. Okay, so in the analysis of data for quantification and calibration, if we use only one variable, maybe we are in this level of univariate calibration. And if we use a matrix of data or use simultaneously several variables, we were using the first order calibration methods. In these first order calibration methods, also we have an evolution using first a classical least square method coming from the most famous law now in opticochemical methods like the Lambert-Beer law. And then inverse least squares, principal component regression, partial least squares, the most used method used in calibration now, and then the second order or multi-way analysis of our data. So the goal of this presentation is to show you some difference between these kinds of methods and to see some applications. Okay, the question is why to use multivariate calibration? I have here a representation of the Lambert-Beer law. Absorbance is a signal response in function of concentration and constant and also a path length of a line. Maybe you know about the Lambert-Beer law, but this is a simple representation of the Lambert-Beer law for several samples using matrix or vectors in order just to align. Okay, so in this kind of method, the absorbance or signal depends on this concentration. But in most of methods used now in calibration, in multivariate calibration, it's on the contrary. It says that concentration depends on the signal because signal has less error, okay? So, but why to use multivariate calibration? I can explain that using just a very simple data set. In this data set, we have two measurements of independent variables, or for example, wavelengths or so on, and one response and two variables. We want to make a regression, simple regression, using this X matrix and Y matrix. X matrix is called error here, and we have two variables and here one response. So if we have if we use univariate analysis, we are using just one column of this matrix, for example, the first column. And if I do a regression between this first column and the response, I will have this relationship. Okay, it's good. Here I have the equation, linear equation, and if I use the second one, the second column regarding to this y vector, I will have this correlation. It's not so good. The error value is low. The distribution of samples is randomly set. So it is not enough to calibrate a y. So if we use both variables at the same time using a bivariate analysis, I will have these results of calibration. So it's absolutely different if I use only one, okay? So this is the advantage to use calibration methods using multivariate analysis. So in simple analysis or simple matrices or simple samples, the use of monovariate analysis could be enough. But in complex systems like the foods, for example, it's impossible because it's very probably that we have some signals overlapping or interference with affecting the signal of the analysis of interest. So in these complex systems, a single measurement is rarely sufficient to describe a system in terms of a quantitative analysis. So we have two options to follow: classic or inverse calibration. Classic, like the Lambert-Beer law, it's based in the calibration of absorbance or signal depending of the concentration, like this plot. Here we assume that the error is in the signal, but now we know that the equipment instrument has less error than the error produced by the analysis of the sample pretreatment and procedures, diverse procedures using to separate the components. So the real information that we have about the analytical process is that error is in the concentration determination and not in the signal of samples. So this assumption corresponds to the inverse calibration, and this is the fundamental of the multivariate methods used like PLS or PCR based on principal component analysis, but for calibration, for quantification, okay? So this is a chart flow to understand which method is better for our data. So the question here is if all the substances spectroscopically active are known or not. If we know the chemical composition of our samples, it's to say, if I know how many components I have in my sample, and the answer is yes, the CLS classical least square or extension of the Lambert-Beer law will be applied or could be applied. So, but if I don't know how many components has my sample, the answer is not. I have another question to answer. How many variables or wavelengths I have? Is it small or is higher? So if the number of variables is low, I mean less than 7, 8, we can follow the route of the multiple linear regression or MLR methods. Okay, this is the simplest method to calibrate in multivariate calibration. This method has a few information about the variables, but maybe it's enough. So, by the contrary, if we have a lot of variables, like is the case of the spectra, we need to use methods based on reduction of variables. For example, using a first step like a PCA, but the methods based in PCA for quantification purposes are PLS or PCR. So we choose this kind of methods of reduction of variables. So I will describe briefly with an application this method, multiple linear regression, in the determination of the ethanol yield produced from wood. The wood is submitted for a chemical pretreatment in order to separate the components of wood that are glucans, hemicellulose, and lignin. These components could be affect the ethanol yield in a positive or negative way. So we need to establish what is the ethanol yield obtained from one sample with determinant amount of hemicellulose, cellulose, glucans, before a very tedious and time-consuming saccharification fermentation process to obtain ethanol. It means that without without application of saccharification and process, we know the chemical composition with high potential to obtain ethanol. Okay, so we have just three variables, glucans, hemicellulose, and lignin, and we submitted this kind of data to a multiple linear regression, and I obtained an answer like ethanol yield, and one equation give us information about the contribution of each component. For example, here, glucans is X1, hemicellulose is X2, and X3 is lignin, and I can see the negative effect of X2 and X3, but if it's logic, if we have more glucans, we will have more glucose and then ethanol yield. So this is the regression using only glucans. This is the regression only using hemicellulose, and this is a regression using only lignin content in percentage, and this is a regression using the three variables at the same time, as example of the MLR. And this is the information that this method gives us. So, but if we have more complex systems, I can use another kind of method, and why initial method of first order is the classical least square CLS. So here I show you some application. This is application, very simple application, because we have three compounds here: dinitrophenol, 2,4-dinitrophenol, 2,5-dinitrophenol, and orthonitrophenol, and we have the spectra of each component. And the spectra of each component shows a great overlapping of those compounds. And if we use univariate calibration, it will be impossible to quantify the compounds in each sample of mixtures of compounds, because the signal is affected by the signal of the other compounds. So it's very difficult. The maximal wavelength here with the absorbance is practically the same. So maybe it's impossible to solve this problem with univariate calibration. So we will prepare five samples, here are the samples, with different concentration of each compound. It's a mixture, okay? And the mixture will be analyzed by a spectroscopy, visible spectroscopy, and then the spectra will be recovered, and here we have the 5 samples of mixtures with the spectra. Totally overlapped. It's impossible to estimate 2,4 or 2,5 dinitrophenol in an independent way. So using this data as X metrics, and then applying this simple equation where absorbance is equal to X multiplied by a matrix K that I don't know, will be possible to quantify. How is possible? So I have the observance from the instrument. I have the X matrix with the concentration that I use in the calibration of standards, and I will obtain this value, and then I will use the same equation for the prediction of a new mixture. How? I measure the absorbance, I use the key, use it in the first step, call it calibration, and I can calculate the concentration or predicted concentration of these components, okay? But if I plot this K matrix, I can also see the spectra of each component, the spectrum of each component, even if I didn't separate physically the components in the sample. It's just a mathematical solution, but if I compare the mathematical solution or the plot of this K matrix with the original spectra, are exactly the same, okay? This is a perfect correlation between the two spectra, but there are a problem. That CLS is a very, very, very good method to quantify overlapped signals. It's very good to quantify with less error this component, but the problem is that I need to know the dimension of this matrix K. So it's impossible in the real life, especially in food analysis, where the matrix is very, very complex, okay? So this method will be discarded if I don't know the composition, the chemical composition of samples. So I require a non-recurring method to solve this problem. Partial least square is a good method because use reduction of variables. This is important factor because reduction of variables means that I can use something like principal components, and I can use a high number of variables, such is the case of spectra, and use remotion of non-informative signals and non-informative values of this X matrix. It means the error or residuals of X matrix is calculated, but also the answer or the concentration matrix will be used in order to remove the irrelevant information of this matrix. It's very difficult to understand, but it's possible. We can remove the error of the data, the instrumental data, but also we can remove the error of the concentrations, okay? So in this case, inverse calibration is used. It's not a direct. Classical CLS is a direct calibration method, but partial least square is an inverse multivariate calibration, okay? So the difference here is this the composition, like the principal component analysis mathematically is very similar, but the principal component analysis gives us principal components or factors or vectors, and in this case, these vectors has another requirement. These vectors could be very, very, very correlated with a concentration. So in PCA, we want to maximize the information that each vector gives us. So here, that's not enough. We need to extract the maximal information of our data, but we need that this vector will be absolutely correlated with the concentration of the samples. Here, Y matrix is the concentration values of a sample. So we here in this method as input two matrices. One matrix with our data and one vector or matrix with the concentration. So we want to correlate them together, but we will find some new variables called principal components, but in this case, the name exactly is latent variables, which are correlated with this concentration, like in this graph. So here we have so many possibilities to find the vector or the principal component, but I want to find the vector which is correlated with this line. Okay, this was the best vector. That's not. This is orthogonal with a concentration. This line is the concentration. Okay, so in this moment, I had the latent variables which are know also like partial list components. Okay, so every calibration method needs 3 steps. The first step is calibration. It's used to use samples with concentration that we know, and this equation summarizes the relationship between the X and Y matrix. This is very simple. Y is the dependent variable, X is the independent variable, and this is the equation that we need to follow in order to find B. B is now the regression vector and is calculated using the pseudo-inverse of X passed here, and we can obtain B. Then we can use this B obtained in the first modeling where we know Y and X, and use this B in order to analyze another sample of validation. We are using here the spectra. We multiply the spectra by this B value and obtain a predicted concentration. Okay, so we can compare the predicted concentration with a real concentration because we are using a validation set. So I know the real concentration, and this difference will give us the error parameters. Okay, there are many calculations of error parameters that I will show you later. So then this model is validated. If the errors are acceptable, are good, or are so good, this model can be used for future prediction. How it works the future prediction? I have the spectra of the unknown sample. I multiply this spectra for the vector of regression, and I obtain the predicted concentration. Okay, this is very simple. So we have here the analytical figure of merits used in multivariate calibration, to be exact, in first order calibration methods. And this is the real value of concentration, and this is the predicted value of concentration. So this difference can be submitted for a similar form that, like a standard deviation. In multivariate calibration is called RMSEC, that this is the error of calibration, sorry by the Spanish. So this is the error of validation. Internal validation is the root mean square error of calibration, root mean square of error of cross validation is the internal validation, and this is the calculus of the root mean square of error prediction, okay, which is the external validation error. So, and it's the number of samples, and key here is the number of latent variables in calibration, and we usually plot the real or nominal concentration and the predicted concentration to see a correct relationship. So the points on the line, it's not usual in multivariate calibration because the model is overfitting, if we see that, because it's a good calibration, but not necessarily a good predictor. So we need a good prediction abilities of the models, and the models has to be robust. Okay, so analytical figures of merit like sensitivity, analytical sensitivity, detection limit, quantification limit. It's a more complex, and even it's an area of chemometrics too. They determine the analytical figure of merits. But we can calculate that about using the regression vector of the methods. So, okay. Now I will show you some application of multivariate calibration using PLS, the reduction method. And in this example, I want to show you the estimation of polyphenolic content, antioxidant capacity, and alginate content obtained from the analysis by near-infrared spectroscopy of 2 brown algae used here or shown here also in the first in the macrocystis in Lesonia spicata PCA. So now we are using the same spectra that we used for PCA to quantify these properties using two ranges of infrared, near infrared, but also mid-infrared spectroscopy. The first are the mid-infrared models, and then the NIR spectroscopy methods. So we can see here one table describing the errors of our models, and here we have, for example, the content of polyphenolic, antioxidant capacity, or alginate compounds with a pre-processing transformation using the number of latent variables or PLS components, the number of samples used to generate the model, the number of samples which our model used to validate the model, the explained variance, the range of concentration or the range of each property that I'm measuring, and the errors of calibration, cross-validation, and prediction with a corresponding regression coefficient. So we can see here that the calibration are good, but maybe in univariate calibration it was a disaster, but here in multivariate calibration, no, the results are very, very good. So maybe the most important factor here is to see the error obtained in the prediction of future samples. For example, here, this model has a 2.9% of error, 0.1% of error in this range of the property analysis. So the advantage to use these methods in this case, in this publication, with the use of chemometrics, is that we don't need to make any sample pretreatment. We just acquire a spectrum of the sample, and then we can see the antioxidant capacity or polyphenolic content and so on for a biomass characterization. And another information that we can obtain from this analysis is the regression vector. The regression vector, yes, is a mathematical matrix that we need to make the validation and prediction, but has chemical information too. Remind that chemometrics try to have most information of our system. So we have here this chemical information. In the regression vector plot, we can see the variables, or in this case, the wave numbers or wave length that are most important for the quantification. For example, here, this has a little of noise. Maybe the model could be imperfect, but it's okay. I can see here, because we use second derivative, that carbohydrate bands are very important for this quantification too, and another bands. No? Here also, in antioxidant capacity, alginate contents, I can define or I can identify the bands most important. So even in mid-infrared and in near-infrared spectroscopy. The information from mid-infrared spectroscopy, usually it's better than the near-infrared spectroscopy, and this is the parameter that we need to check in PLS. So regarding another techniques to use with multivariate analysis, I want to show you something about chemical imaging. So yesterday we heard about the magnetic resonance images, and it's very interesting because it has a very good resolution and another ability to obtain different depths information. But in infrared spectroscopy, we have another possibility to mixture an imaging with a chemical information. Today in the morning or in the afternoon for you, in the presentation of Michael, we have a lot of information about NIR, and yesterday we have with Rob information about the images, and now we have a mixture between two images coming from the infrared spectra, and this is called hyperspectral imaging for us, and it will be done using different vibrational techniques like Raman spectroscopy and also mid-infrared and also near-infrared spectroscopy. So in this kind of information of data, we can apply another chemometric techniques that I mentioned. For example, one specific technique is the multivariate curve resolution in order to separate overlapping signals obtained of this method. So today I heard some question of Hosnein about the possibility to obtain more information about the spectroscopy methods in order to see which component is causing the response, because I have a mixture of signals or components, but it's possible to resolve or separate this information into assign to one response to a specific component. I think this method could be interesting for this purpose. Multivariate resolution with alternate least squares is a very known method used for imaging spectroscopy and other methods like, for example, chromatography methods, where there are overlappings of signals. So the mathematical principle is similar, very, very similar to the PCA. We have a matrix, now it's D matrix, it's the same X matrix, really, it's just notation different because we are looking for another output. But the equation is practically the same. The matrix of data or spectra with m samples and any wavelengths, for example, or other properties or rotation times, is discomposed in two matrices. One matrix will be called not scores, but a concentration, relative concentration, because it's not a concentration, the real concentration, but the relative concentration multiplied by a new matrix called no loading, but a pure spectrum. So this is the advantage of curve resolution, that I have a mixture of signals and I will resolve these signals to obtain a pure signal of one component, okay? Which component? The P component. That means that I need to know how many components has my system. This is a question like CLS, because in CLS I need to know how many components, and this is only the word of pharmaceutical analysis, but food, no, it's impossible. So I don't know, I don't need to know how many components I have. So if I have an LG sample and I have a lot of components in my LG sample, I can resolve the signal of the total spectra in the contribution of the individual components. And then I can plot this matrix as pure spectra and see the spectra, okay? So mathematically, at this point, it's similar to PCA, but this method applies constraints in order to obtain results with chemical meaning. For example, that the results cannot have a negative result, because negative concentration is impossible. Negative spectra, it's also not common, it's not a real spectra, nor in opticochemical method. So these constraints will assure a good solution, mathematical solution of this decomposition. Because a combination of C and S has a lot of solutions, a good solution mathematically. This problem is known as rotational ambiguity. So we need to solve this ambiguity using constraints, okay? So then we can estimate some error parameters that I will not talk about that, because there are only the relation of this error regarding the original matrix. I need to obtain a lack of fit very low and an error coefficient of regression very high. So this is the application of this method. I have my matrix D and I decompose the component, but now I will apply this not only through a set of spectra, but a set of spectra of the imaging. So I will scan my sample with a detector, with an array of little detectors, like is the case of CCD detectors, And yesterday or last yesterday, I don't know when yesterday, we talked about point-to-point scanning, and this is very tedious, it's very slow, but we can use also another kind of detectors, linear or focal plane array of detectors, and obtain an image, and each pixel will have associated a spectrum, okay? So each pixel will be a row here. Each pixel, pixel 1, pixel 2, pixel 3, pixel 1000, 10,000. We have images with the sense of thousands normally in an infrared image, okay? So this matrix will be submitted to the composition in C and S, and then I will have the relative concentration of each sample. And I will array again this column for the first component, second component, third component. I will looking for how many components has my system according to some mathematical estimation based on our method called singular value decomposition. And I can find how many components have my sample, and each column will be the scores or the relative concentration of each component, and I can array this score, this relative concentration element to the dimension of my image to generate this kind of graphics. So this is the distribution of one component, another component, and this matrix will have the spectra, pure spectra of component 1, pure spectra of component 2, pure spectra of component n, and so on. So here we have an application of Fourier transform infrared imaging and multivariate analysis for a direct identification of principal polysaccharides in broad C widths. Also using, I think I don't remember that, Lesonia or macrocystis, it's one of them. So I show you here the hyperspectral imaging. So we can see here 3 components after the application of the method that I will be discuss better here. Where this is the equipment that we use to do this analysis. This is the image, okay? This is the infrared spectrometer. So we have here a comparison between PCA and MCR. So this is the same mathematical decomposition in the same matrix, but this method uses the constraints, non-negativity constraints in concentrations and spectra. So we have here the difference. The PCA tell me that I have 3 or 4 components, I don't know, and this is the loading plot. In the loading plot, give me information about the importance of the wavelength. So I see the first component. This is a hot bar, scar bar. So you can see in red the accumulation of one component, and this component, for example, in this zone, in this blue zone, is not present practically, okay? And here, the red zone is assigned to the second component. Here, that this zone is assigned to the third component, and here there are other components because this component is in blue, okay? So it's difficult to interpret scores and loadings plots from a PCA in an image analysis, because I see this loading and I just can conclude that this is important, this band 2 for this component in red, so this negative band is not important for this component in red, but is very important for this place in blue. So it's very difficult. So, but if I use MCR-AS, I can detect how many components I have. In this case, I have 3 components, and I have as output the pure spectra of the sample. So I can see the spectra, and I can interpret this spectra using bibliography or reference spectra or another alternative, and to see that this component, chemical component, is distributed in this way. So for example, it's not here, but it's in this part. So I can localize the chemical compounds, but I also identify the chemical compounds, okay? So if I make a mixture of all these spectra, I will have the spectra of original sample. It's a mixture, a lot of spectra. And this is the individual spectra of each component, and this is the localization of each component too. So if I have my pure spectra, now I'll be able to identify. This is the same case that I have here, the same sample. This is the steep medulla of edges, and I have here the spectra and the number of the bands, and then I will analyze these bands and who compound has this band. A lot of compound has the same bands, but the profile, the chemical profile in mid-infrared under 2000 Y number, it's the fingerprint region of the mid-infrared spectra, so I can assign the identity of the compound. And after an analysis of each spectra obtained mathematically, I can conclude that this is mannitol, this is fucoidens, this is alginate, okay? So this interpretation is easy because you need each band and then compute in this gas and so on. So, but it's possible. I mean that we have many pixels analyzed, thousands and thousands. It's impossible to see one signal for each pixel just using your time or patience. You need more sophisticated strategies of data analysis and multivariate resolution in case of images is that maybe the best option, okay? So we can identify the sample. So even if we don't have images and we have only a spectra without images, it's the same. You can obtain also the identity of the compounds, okay? Today, I found this paper, Detection of Chocolate Power Adulteration with PENAM using near-infrared hyperspectral imaging multivariate resolution. I am looking for MCR applications. And this is the last explanation that I say here about that. Even if you don't have imaging, you have the spectrum. So you don't have necessarily localization, maybe. You just need to see the relative concentration elements or scores. I'm plotting now the elements of these metrics to see this distribution. And the objective here was the detection of the adulteration of the chocolate power. So we can here see two groups principally, here one group and another group. And here is the pure peanut and then the adulterated sample of chocolate. So you can establish different groups and you can see. But the application of MCRLs to the data give us as results, as output, the spectra of pure spectra of cocoa, okay, of sucrose and the interference. So you can see here that even if we don't have the pure spectra of the components, because you don't know how many components has your food, it's possible to find so many components. Maybe here we are plotting or we are working just 3 components, maybe there are more, but with less variance. And we can plot all the spectra until to find noise, okay? So we can resolve a mixture of signals between the contribution of each compound independently. So, this is slide. This is from this interpretation because to assign to mannitol fucoidens or alginate is not easy, but we use a little of bibliography in order to see the identity of the compounds. Okay. A similar example is shown here using multivariate resolution in the evaluation of the microscopic distribution of one active principle fluorophenical in feed pellets for salmon using infrared imaging and also the mentioned method, MCR. So in the works that we see here, okay, we can find the pure spectra of the components and then interpret them and to assign these components to one component, but chemical compound. But here we have the fluorophenical standard. It's different because we have a pellet using for salmons as food, but also as a drug. So we have the fluorophenical standard, and we can looking for this fluorophenical in the food, okay? And this pellet has around or even below 1% weight of concentration of fluorophenical in the pellets. And the pellet has a dimension about 2 centimeters and 3 centimeters, depends, okay? Depends of the salmon size. So, but the concentration is very, very low. So we are looking for a sensitive technique to localize the fluorophenical, and we scan the sample using mid-infrared spectroscopy, and the scanning gives us an image, hyperspectral image, because each pixel has associated one spectrum, and then we use all the spectra to be submitted to a multivariate resolution. And then the output give us the pure spectrum of the components, and we are looking for exactly the fluorophenical spectrum. The fluorophenical spectrum is in black, and the blue spectrum here is a mathematically obtained spectrum of one compound present in our sample. If we see that, if we see both are very, very similar, especially in these images, it's practically the same. So we assign this compound to fluorophenical. And the blue line is just a mathematical or chemometrical solution. So it's very, very interesting because the compound is in a low concentration. So this is analysis in the surface, but we can also cross the sample and to acquire the fluorophenical distribution in the inner part. So here is clear that the inner part has most distribution of or more fluorophenical percent than the surface. Okay. So this is regarding the multivariate resolution methods, and this is like PCA, a matricial method, and use a property of analysis calling the bilinearity method. I need just one matrix, but there are more chemometric methods. This presentation is only to show you how many methods we have for each purpose, but there are a lot more, and I want to show you multi-way analysis methods in order to open the mind to another technique of analysis of data analysis to incorporate to the project, maybe with another techniques. So multi-way analysis requires not a matrix, but a cube or other geometrical configuration with more modes. Okay, I don't know how to plot or how graph more higher levels, but this is a second order calibration or second order data with a cube as a data arrangement. Okay, so this kind of methods are very used for technical, hyphenated techniques, like for example, chromatographic, liquid chromatography with GAG detectors, detection, or also in fluorescence where we have excitation and emission spectra. So now we can think in the array of data in a cube where for example, these rows will be assigned to the object, sample 1, sample 2, sample 3, and so on. And this coordinate will be assigned to one mode. For example, excitation wavelength of fluorescence, and this K-axis will be associated to the emission wavelength, okay? So this is the same array, maybe in food chemistry is used, or in food science, is used for sensorial analysis, where we have here the objects. Here we have the parameters that we want to test. And we have here, for example, the analysts or the persons who are recovering information about each parameter. And this is also a perfect cube to analyze the data by a multi-weight analysis, and it's used often. So the most famous method there is the parafact or parallel factorial analysis, that is an extension of the well-known PCA in two-way, but now instead the decomposition of the cube in scores and loadings and loadings. It means that I have just no one scores and loading, but I have now one score and two loadings, okay? So that decomposition mathematically is very similar. I have here scores, A multiplied by G is scores, it's the same, and B is the loadings. So here I have the same exactly, but now I have in place of this matrix G, a diagonal matrix, I have here a cube, and the decomposition will be done regarding two different number of components. For example, if my sample has 10 components, I will have 10 elements here in this zoom, and each element will have 3 coordinates. One coordinate assigned to the scores, to the samples, for example, that this coordinate be assigned to the one mode, for example, excitation spectra, and the other axis assigned to the emission spectra. Or if we are working with HPLC DAG, it could be objects, samples, rotation times, and spectra, visible spectra, for example, UV spectra. And we work with mass spectroscopy, CG, GC, MS, sorry. We can have here the samples, also here the chromatographic signal, and then the spectral signal, okay? So this is the iconite techniques that we need to use this three-way method like parafact. And then parafact as well is a exploration techniques, will give us information about groupings of clustering of samples. For example, if the samples are together because they belong to the same brand of whiskey, for example, we can see that like a plot of this mode A, because this mode is regarding the samples distribution. But I want to see now how many components has this data set, and I can see, for example, the chromatographic profile or the component 1, which is the time rotation of the component 1. Then if I plot this, I will be the chromatographic profile of the component R, just R. And if I plot this data of this dimension, I will see, for example, the UV spectra of the component 1. Here, the UV spectra of the component R. Okay, so this is a lot of qualitative information about the samples, about each mode, where each mode corresponds to an analytical signal. Okay, so in the case of sensory analysis, we can also hear the objects. If the objects are groupings spontaneously, we can see that in the plot. But also we can see if there are relationships, or there are one word that I don't remember, not it's an agreement, something like agreement between the panel. If the panel feels the same or not, they will be grouped or absolutely different, separated. We can see that another mode, and we can also see the difference between the parameters. For example, sweetness and I don't know. I don't remember another parameter, but other correlated. So if we can see all these qualitative relationships between the samples and between also the other modes of the cube. So here we have an application of Rasmus Bro group in Copenhagen using HPLC. Here we have different liqueurs, 24 commercial preparation of St. John's from different continents, and they have replicates and they have origin in country of origin. And this is just a visualization of data. Here is the detector signal, is a UV spectrum, and here we have the chromatographic profile of the sample. So this chromatographic profile is detected or is plotted at determined wavelength, and these wavelengths are plotted regarding one of this time relation, because there are a lot of information here, different wavelength and different rotation times to plot. So what is the output of Parafag scores and loadings give us? Parafag will give us 3 information because it's a cube. So we have these 3 information, the samples, mode 1 and mode 2. And here I have the samples. We can plot the samples, and for example, we can interpret this plot looking for example, this sample. This sample has a high content of the component 2, or also I can see here 3 components, okay? 3 components, blue, green, and red, and I can interpret this plot for each sample, giving looking the signal here, and we can see, for example, that this sample has a lot amount concentration of that of the component 2, but low of the component 1 and component 3. Okay, this sample 2, but for example, this sample has low content of the component 3, of the component and less of the component 2 and 1. So which component has associated a chromatograph and a spectra? So this is the chromatograph of, for example, the component in blue, the 1 is very rare, and the best maybe is the green component, the second component. This is the rotation time, and the third component has this is not normal in chromatographic because could be a pure component. So we need just 1 peak in chromatography. So we need to improve these results and apply, for example, another constraint of the result in Parafag, and to say, okay, please give me a mathematical solution that the chromatograms has only 1 peak, no more, because this is 1 real component, okay? Because this is a mixture even, okay? So this is the possibility to see the spectrum or chromatograph in the case of Parafag application. And this is the spectra of component 1, component 2, and component 3. So we, in any moment, we are measuring the pure profile, chromatographic profile of each component, because I'm working with food. It's impossible. And we are working here with, in any moment, we acquire a UV spectrum or spectrum of each component individually. No, this is a mathematical solution, but if I apply constraints also in Parafag, it's possible to apply constraints, I will have the profiles, the chemical profile of each component detected in my sample. So I don't need, in this case, sample preparation in order to eliminate the interference. Okay, so it's possible too. To finish, I want to tell you about the second order calibration methods, and the most famous method is the UPLS method, unfolded PLS. Just to remind, the unfolded step is desdoblado in Spanish. Unfolded concept is that I have a matrix and I can unfold this data to a vector, putting the column under the first column and then under the second column and so on. And we have here now a vector, so I reduce the matrix to a vector, and then we can use, for example, univariate calibration, okay? And in chemometrics it's the same. I have a cube, and this cube is unfolded to a matrix. I put each face of the cube under the other face, and I have now a matrix. And if I have a matrix, now I can apply bilineal methods like PLS, the simple PLS, and this is X matrix, and this is the concentration on all the samples, okay? And I will prefer PLS, and I have now a second order calibration. So my question can be why I will use second order calibration if it's more difficult, and I can use first order calibration and it's better. But second order calibration has an advantage, very known. The advantage of second order calibration is that I can quantify one analyte in presence of the interference, okay? So, but this is also the advantage of the first order calibration, is the same. Yes, but in the first order calibration, I can quantify my analyte in presence of the interference, but the interference must be there in the calibration samples. For example, if I analyze a chocolate sample, all the chocolate sample will have the interference. So I will build my mathematical model using PLS, a first order calibration with the interference, with the chocolate. But if I have one sample to predict, for example, I don't know which prepared in chocolate, but if I have one sample, which one interference or two interference, which were not in the calibration set, my model will not work well, okay? So this is the disadvantage of first order calibration. So I need to include all the interference in the calibration, and my prediction sample must have the same interference, okay? But in the second order calibration, I have another advantage. So I can analyze my compounds in presence of interference, but maybe my sample has another interference that was not present in my calibration set, and the model will work okay, very good. And this is now as the second order advantage, okay? But I need an hyphenated method or a cube of information. One method is not enough, okay? But I can use my mathematical model to quantify one analyte in presence of no modulated interference, okay? So there's not the unique method in two-way analysis. We have another well-known method, and the name is NPLS or N-way PLS. And if this method use a step of unfolding of data to use finally an X matrix, here I don't need an X matrix to apply the quantification method, but I will use the cube directly. How? I will use parafact, the decomposition that we will see here, and this value of this axis or these scores of the decomposition of parafact will be plotted. The scores, each sample has a score, will be plotted regarding the concentration of this sample. In this step, called pseudo-univariate analysis, in this pseudo-univariate calibration, I will have an equation, a linear equation. So if I have a new sample, I will submit this sample to Parafat. I will have the score value. In this score value, we'll be looking for in this equation, and I can calculate the concentration, the real concentration of this new sample. And maybe I can obtain the second order calibration. The use of hyphenated methods or the cube of information does not guarantee the second order advantage. So maybe with UPLS, I obtain the second order advantage, but with NPLS, not for one sample, but for others kind of sample with Parafa or NPLS will have the second order advantage and not with UPLS. Normally this is used, for example, for spectroscopy, fluorescence, chromatography, it works very well. But in this case, I need a trilinearity, so I need a variation in a simultaneous way of 3x's in the data set. So I have here quantitative information, okay? So this is regarding the NY methods. I think I on time. Just to remind about this presentation, a suggestion, just make a PCA even you can of your data before more complex analysis, because in the PCA analysis you can decide if the reduction method works or not works, okay? And then you can choose your mathematical or chemometrical methods for following steps. Then also you can classify your samples, and even you can classify your pixels. If you use a spectroscopy with imaging, you can classify the pixel and say, okay, this pixel and this image and this sample belong to the class, I don't know, interferent or sample or principal or active ingredient, I don't know. So, but you can do it with pattern recognition methods. So you can also quantify one compound in presence of interference. Your interference could be in your calibration step, and this is the first order methods, or couldn't not, and this is the case of the second order calibration methods. So you can quantify in presence of non-modulated interferences using the second order advantage. So I think that it's better to use just not one variable, but a lot of variables, because the results are improved. So I want to finish my presentations. I just junior means strength. So I recommend multivariate analysis for your data.